Hydrologists divide the Earth into two types of materials based on how well they can transmit water: aquifers and confining units. You'll sometimes also hear the word aquitard or aquiclude instead of confining unit, but most modern hydrologists use confining unit. An aquifer is defined as a package of rock or sediment that has significantly higher permeability than surrounding units and can thus store and transmit useful quantities of water. Note the term relatively in the definition. In some areas, such as rocky regions where almost all the rocks have relatively low absolute permeability, what's considered an aquifer is simply the unit with the highest permeability. This same rock might be considered a confining unit in other areas where rocks or sediments of much higher permeability are common. A confining unit is the opposite, a package of rock or sediment with a low permeability that doesn't permit much water to pass through it. Since aquifers have to have a relatively high permeability, they tend to consist of unconsolidated sands or gravels, or sometimes rock with a high secondary porosity, like limestone. Confining units typically consist of silty or clay-rich sediments or rocks. Aquifers and confining units are not randomly distributed in the Earth, since most of them are found near the surface in sediments and sedimentary rocks. In many parts of the Earth, sediments and sedimentary rocks are arranged in relatively horizontal layers, and since the type of sediment determines the permeability, aquifer and confining units tend also to be arranged in relatively horizontal layers. If you look at cross-sections from many parts of the world, especially near coasts, you'll find that the subsurface consists of a stack of sediments and sedimentary rocks piled one on top of the other and in a relatively horizontal orientation. These layered sediments and sedimentary rocks create a stack of aquifers and confining units with the same semi-horizontal orientation. Water moves into and out of this stack of aquifers and confining units through the water table that forms its upper surface, moving rapidly through the aquifers and slowly through the confining units. Although there may be many aquifers in a stack at any given location, there is only one unconfined aquifer, which is the topmost aquifer and the one that's hydraulically connected to the surface. The unconfined aquifer is the only one that does not have a confining unit as its upper boundary. Instead, the water table forms the upper boundary of the unconfined aquifer. And because the position of the water table depends on inflows and outflows of water to and from the surface, its position can change throughout the year. This means that the thickness of the unconfined aquifer can change too. Also, since the unconfined aquifer is where most groundwater is exchanged with the surface, there is often a significant component of vertical flow, so that the head beneath the water table is not often the same as the water table. For example, in this diagram, the piezometer has been installed in a recharge zone where the head beneath the surface is less than the elevation of the water table, indicating downward flow. The most common type of aquifer is a confined aquifer, which consists of an aquifer layer sandwiched between two confining units. As shown in this cross-section of Florida, there may be many confined aquifers stacked one on top of the other. In this diagram, the uppermost confined aquifer is the Upper Brunswick, and the lowest is the Fernandino permeable zone of the Lower Floridan aquifer. Notice that, unlike the unconfined aquifer, the thickness of the confined aquifer cannot vary. Wells or piezometers can be sunk into a confined aquifer just like they can be sunk into an unconfined aquifer, and the head has the same meaning, the elevation of the water level in the piezometer above datum. Notice, however, that in a confined aquifer, the head is always at an elevation higher than the top of the aquifer. This means that the water in a confined aquifer is under pressure and will spurt up if you poke a hole in the top. There are some simplifications we can make about confined aquifers that in some ways make them easier to study than unconfined aquifers. This first is that the vertical variation of head at a given location is usually very small. In other words, if the head at this location is 15 feet, then the head will be about 15 feet at any depth within the confined aquifer at this point. This means that if we want to measure head, it doesn't really matter how deeply we sink the piezometer into the confined aquifer. Any depth will do, since they all give about the same value. Here I've shown that result at three different locations. Notice that the head can and usually does change in a horizontal direction. It's just in a vertical direction that it doesn't change. If we wanted to determine the direction of groundwater flow, we could sink two piezometers into the confined aquifer and observe the heads. Notice once again that it doesn't matter that the piezometers aren't installed to exactly the same depth as long as they terminate in the same confined aquifer. Another thing to notice is that the head in the confined aquifer may be above or below the water table. In other words, the confined and unconfined aquifers act independently and can each have their own flow system governed by the heads of the pore waters inside of them. In this case, the head on the left side of the confined aquifer is below the water table, while the head on the right side of the confined aquifer is above the water table. This also means that there will be some drive for downward flow across the confining layer to the left and upward flow across the confining layer to the right. Heads measured in confined aquifers are interpreted exactly the same as they are in unconfined aquifers. Here we have 3 piezometers sunk into the confined aquifer, defining 3 levels of head. Now imagine doing the same thing for an infinite number of piezometers located at every horizontal location. The surface formed by connecting all these heads and all these piezometers is called the piezometric or potentiometric surface and determines which way groundwater flows in a confined aquifer. In 2 dimensions, the piezometric surface looks like a line, like it is on this diagram, but remember in 3 dimensions it's actually a surface. Groundwater obeys Darcy's law in a confined aquifer just like it does in an unconfined aquifer, so it moves from high head to low head in a direction down the gradient. In this example, groundwater would be flowing from right to left. Notice that the groundwater flow is horizontal because it occurs in a horizontal confined aquifer, while the piezometric surface is distinctly not horizontal. Don't get these two confused. Here I've shown 2 piezometers or wells in a confined aquifer to make an important point. Sometimes the elevation of the head in a confined aquifer is above the elevation of the land surface, as it is for the well on the left. The head on the well on the right is above the top of the aquifer, as it has to be, but it's below the surface of the land. Whenever the head is above the surface of the land, water will spontaneously flow out of the ground and onto the surface. This kind of well is called a flowing artesian well. If an opening is created naturally connecting the confined aquifer to the surface, and the head in the confined aquifer is above the elevation of the surface, then a natural spring results. Manatee Springs west of Gainesville is an example of a natural spring formed from a connection between the confined Floridan aquifer and the surface. The head of the Floridan aquifer is higher than land elevation, so water continuously flows out of the spring and fills a small lake. Because each horizontal location in a confined aquifer can usually be associated with just one value of head, hydrologists often create contour maps of the head in a confined aquifer or maps of the piezometric surface. This map of the upper Floridan aquifer in Florida calls it a potentiometric surface, but in both cases they mean the same thing. Potentiometric, piezometric surface basically mean the same thing. The piezometric contour map can be interpreted much like a topographic contour map, with hills and valleys. In this case, however, the hills correspond to locations where the head in the confined aquifer is higher than surrounding parts of the aquifer. The red X on the map here is located at the 110-foot contour, which means that if we installed a piezometer into the upper Floridan aquifer at exactly this location, water would rise in the piezometer to an elevation of 110 feet. We also know which way water in the aquifer would be flowing at this point, in the direction of decreasing head. This tells us that it has to be moving to the west-northwest, in the direction of the 100-foot contour and then further along to lower contours as well. In fact, it's easy to show that the direction of the gradient vector has to cross the contours at a right angle, and since groundwater is flowing down the direction in the direction opposite the gradient vector, it too has to cross contours at a right angle, always going from high head to low head. Using these 2 simple rules, 1, that the flow has to go from high head to low head, and 2, that the flow lines have to cross the contours at right angles, it's possible to infer the path of groundwater flow within the Floridan aquifer starting from any point on this map. 2 of these paths are shown here in green. Notice that the paths are in general not straight lines, but follow a curved path as they continuously seek lower elevations and cross them at right angles, and that it makes a big difference where you start from.